This is the demo of graphs and topology for chemists, which is GandT on GitHub, which creates persistent homology features for the use in chemistry machine learning. Now, there's a lot of interesting chemistry problems that can be approached with machine learning, such as molecular design, which is useful for drug development, biotechnology, inventing new materials, and understanding biochemistry. Chemistry has some specific challenges, however, such as it's not really known how best to input the three-dimensional structure, which is featurization, and this is the problem PHFs are designed to solve. And also there is the problem that data sets are very small in this field. The method that I choose to use is persistent homology, which is a new area of topology. Topology is concerned with counting the number of topological features, such as a ring seen in X2, or connected regions, such as the 6 connected regions seen in X1 and the 12 connected regions seen in X0. By using this, we can make very small and compact features, and this allows us to use incredibly small and simple machine learning algorithms. For example, the ones I use are 2-layer feed-forward neural networks, which are very simple. We have applied this to various problems. Protein binding is one such problem that's very important because it allows us to figure out if a new drug would target a molecule and would be very good at that. Using the PHF features, we can get about the same answer on this problem, so same small error as the graph convolutional neural networks, which is the state of the art. However, we can do this in 5.5 minutes as opposed to an hour and a half on this problem. And if you compare our results to the state of the art, you can see that we are statistically indistinguishable from the state of the art on this problem and commensurate with the rest of the state of the art using different techniques. Solubility is also very important for drug development, and on this problem we can equal the state of the art, as you can see on the top left of this slide, and these are all neural networks, and you can see that we can use a much smaller and simpler neural network, which means it's cheaper and easier to train. Taking some of these models, published models, and putting them on the same old computer, I was able to run them and see how they compared in terms of training time and energy usage. And as you can see, the PHF models were able to train in 30 seconds as opposed to 18 minutes or almost 2 hours with much smaller energy usage. The GandT project takes in various different molecular structure data and can output CSV and HDF5 files which can be used directly for machine learning, or you can use the example notebooks and PyScripts in this particular piece of software. Now we're going to look at actually using the PHF features, and we're going to featurize the PDB binds, the protein binding data set. So we can load molecules from the file, as you can see, and we put them into these molecule objects, which aren't just a picture. We have the coordinates and the atom types there. To create the persistent homology feature, we start with a point cloud, and this is the protein binding pocket, and hopefully you can see there is a void in the middle of it where the ligand would sit. Then we create a persistence diagram, and here we look at the number of H1, H2 and H0, where H2 is the void, and as you can see, this point here, which is far off the line and therefore very persistent and important, is the void at the center of the binding pocket. We can do the same for the ligand, which is quite similar to benzene, where the most important feature is the ring, which is this H1 feature. We don't actually train on these diagrams. We vectorize using things such as persistent entropy, which converts these diagrams into a set of numbers, and overall we end up with 18 numbers, and the explanation for this is given in the manual. GandT includes a method to make data sets. You put your data set here with your smart strings and any other information you may have, and then you'd want to use the scripts here. For example, for the Delaney data set, we run this. What it does is it reads in the molecules, featurizes them one by one, and then writes them out as CSV files, the data that is, which can be used immediately. And then you can add in extra data that you may have, which is perhaps non-structural, and add that into the HDF5 file, as you can see has just happened there. So you can also use the HDF5 files that come with the package, and for the protein binding we have two data files, a big one called refined and a small one called core. And we can create a data set from these HDF5 files, where we pick out those features associated with the proteins and those associated with the ligands and stick them together. This gives us data that is 36 numbers long. So each vector is 36, which is a very compact representation. And then we can train on this. So we have about 3,000 complexes in our training set. And we have our holdout set here. And I'm just going to train a random forest on this. It will be very quick. There we go. As you can see, the R squared is about 0.9, so it's trained well. The test data, we get about 0.47, and for the core data set, we get about 0.46, which is pretty good. There is code to run repeated experiments, and if you want to do more complicated experiments involving mixing up data sets, then look on GitHub at some of my other projects. To conclude, we find that using persistent homology features, we are able to equal the state of the art for various chemistry problems, and we do this in a very efficient way that is much faster and cheaper. For example, we can take up less space on the disk by featurizing, as you can see on the first line. It is also many times faster for training protein binding problem, which is a difficult problem. And when we measured the energy efficiency by rerunning other people's algorithms on the same computer, we find that the PHF is many times faster and much more energy efficient.